Welcome to Brain Vision.
In this question, we have two stars that we consider as black bodies. We are given that the energy that is radiated by these two different stars is the same. And we want to find what is the temperature of the hotter star. Right, so this cooler one has diameter 3 times of the smaller star. So basically its radii is also 3 times, right? Well, from the Stefan-Boltzmann law, we know that the intensity of radiation emitted by a black body is given as a constant sigma multiplied by the temperature to the power of 4. This is the intensity, right? Not the total energy. The total energy that's irradiated by the entire star, I'm going to assume it's a sphere, would be equals to the surface area multiplied by the intensity. Should be, in this case, taking 4 pi r square times sigma times t to the power of 4. Right, so this is for the smaller star. So this is actually T prime. Right, because it's not actually the temperature of the cooler star. Right, so we're going to use the cooler star to be T. For the cooler star, the energy irradiated will be 4 pi 3r square times t to the power of 4. Now we equate this to the energy of the hotter star. And what we want is to find T prime in terms of T. Right, so we get rid of the constants. We can get rid of r square. Right, so we're left with only 9. Here we can get rid of the sigma as well. Sorry, there's a sigma constant in here as well. So what we're left with is 9t4 is equals to t prime to the power of 4. And therefore t prime, we just take 9 to the power of 1/4, and we should get around 1.7. So this is the temperature of the hotter star with respect to the temperature of the cooler star. Next, to find what is the ratio of the wavelengths or of the peak intensity for these two different stars, we need to use the Wien's displacement law. Right? The Wien's displacement law basically tells us that the wavelength, peak wavelength emitted is equals to a constant, let me just call that K, divided by the temperature of whatever planet or object that we're looking at. So in this case, to take the ratio of the peak wavelength for our cooler star divided by the wavelength of the other way around, right? The peak wavelength of the hotter star divided by the wavelength of the colder. So B, temperature of the cold divided by temperature of the hotter star, which we know the colder one is just T, whereas the hotter one is 1.7 T. So this gives us about 0.58 as our ratio.